Okay, welcome everyone. My name is Sean. I'm the team captain, and we're going to get started with our workshop here today. Hopefully everyone brought balloons for our experiment. And without further ado. So in this webinar, we're going to go over these contents. We're going to start with an introduction and information about our team and its members. And we're going to do this balloon experiment. We're going to take these balloons, we're going to blow them up and set them free and see how they fly. Then we're going to talk about rockets, or how rockets fly better than balloons. Then we're going to do a little demonstration on how to build and launch rockets. And then we're going to have some audience-led discussion at the end. So if you have any questions or anything you want to talk about more, that's the time we'll do it. Okay, so I'll do the introductions. Hopefully Jonathan can join us for the rest of the meeting soon. So we are the rocket team representing New Jersey in several national rocketry competitions. These include the NASA Student Launch Initiative, as well as the American Rocketry Challenge. We've been doing competitions for 2 years, or well, 1 year now. We started with the American Rocketry Challenge, where we placed 17th place and highest from New Jersey. Since August 2021, our team has worked hard to become one of the leading teams in the nation, and we are proud to be able to showcase our work and dedication with you all today. So we'll do some introductions of our members we have here. My name is Sean. I am the team captain. I started the club with the help of the adult leaders, and it's been a nice journey. The only member not present here today is Ryan. He's our vehicle lead for the NASA student launch. And with that, I hand it over to Holt, who is our NASA student launch safety officer.
Hi, yeah, I'm Holt. I've been doing rocketry on and off for a bit over a year now, and I personally think it's a great way to have fun, to learn, and it also has some great opportunities now and in the future. Next, I'll hand it over to Maya to introduce herself.
Hello, I'm Maya. I joined our rocketry team in late 2022. I'm very glad I joined, and my experience so far has been great.
It sounds like Jonathan is back. Jonathan, can you introduce yourself?
Sorry about that. I joined recently, a couple months ago. I joined because there's just something about rockets that I like. I've always liked space, and I guess it fueled my passion for rocketry.
Thanks, John. And when I said members, I meant the student launch members. We might have other club members here, or just other people present, but it's just the NASA student launch team presenting here today. So next, we're going to talk about the project goals of the NASA student launch. So this started a long time ago in 2021, where we wanted to compete in the NASA student launch. But unfortunately, we quickly found out that we were too late for that season, and we had to qualify first through a competition like the American Rocketry Challenge. So in 2021, late 2021, we registered for TARC, which is the American Rocketry Challenge. And we were required to place top 25 out of up to 1,000 teams, and so that we could qualify for the NASA student launch. And we set out to do that, and we were able to achieve that. So then last summer, we started planning for the NASA Student Launch Initiative. And we were putting together our team, getting everything ready. And then in August, the competition started. They put out the handbook and the request for proposals. So anyone interested that's eligible can submit a proposal, their plan for the competition, how they're going to do it, and a lot of information, safety information, so that the competition runners make sure the teams that they select will be safe and will achieve their goals. So we were one of 18 high school division teams that were accepted, And there were 69 total teams, including all the universities when the competition started. And now that brings us to our main project here, which is building the main rocket and the payload. So since October, when we were accepted, we started developing and building this rocket. We had 2 reviews so far with NASA to make sure our plans are correct, they meet the requirements, they're going to be safe. And fast forward to now, we've recently flown our rocket for the first time, and we're looking forward to the next milestones here. So what we have next, we submit a flight readiness review presentation where we present to the officials and tell them everything we've done, tell them exactly what we have made. And that's the final review before we go to the end of the competition, the finals, which are in Huntsville, Alabama at NASA's centers there. So all the teams that are remaining get to go there. Lots of activities for a week. In the end, everybody flies their rocket, flies their payload, and then the scores that you report, we submit those, and that's the end of the competition. The last milestone, last review is in May. In that review, we submit the data, we submit everything we got from that last flight in Alabama, and then the judges will go through, score everyone, and the winners are announced. The middle school division, which we are doing, is not scored, but the university divisions are. So that's the main project, the main, the point of the project. But in addition to that, building the rocket and flying it, there's also one third part, which is the STEM engagement. Every team, every 65, 70 teams that were selected has to complete a very impactful STEM engagement program. Each team, this might be 5, 10 people each, they have to engage 250 kids talking about science, technology, engineering, or math, and they have to demonstrate that in a very hands-on way. So that's why this competition exists. It's to help teach and educate the future employees, scientists, and all that. And that brings us here. This presentation, the rockets, the demonstrations we've done before, those were all for this requirement to teach new people about rocketry and science. And with those introductions out of the way, does anyone else have any questions about our project or any of us? Okay, Holt, would you like to start with the NASA Jet Propulsion Laboratory balloon experiment?
Absolutely.
This experiment was created by the NASA Jet Propulsion Laboratory. You might know them as the people that worked on the Mars rovers and many other big NASA projects. So get your balloons ready and Holt will take it away.
All right, so I'll assume all of you have your balloons. What you're going to want to do is blow into the hole, obviously, and inflate the balloon.
Can we pull Holt up for the Zoom call? Centered.
All right, once you have your balloon inflated, you don't want to tie a knot on the end of it. Instead, you just want to pinch the end of it so the air doesn't come out. Then what you're going to want to do, you're going to hold it out in front of yourself with one hand, just holding the hole. And then for now, we're going to have the hole facing to our left arm. And then you're simply going to release your left hand. And then you'll have seen that the balloon goes
You're unmuted, Hope.
Oh, sorry. So you'll see that your balloon does not, in fact, stay going right the entire flight. It goes up, down, left, right, down, or I already said down. But as you could probably see, it's not very stable. It doesn't go in one direction.
Holt,
And-
I see a purple balloon
somewhere.
Purple
Oh,
balloon.
I think it escaped.
Oh,
If anybody,
Should we stop the screen share maybe so that we can see everybody's progress with the balloon?
if there's anybody who has a balloon on hand that would like to
Right.
demonstrate for us. So I know I saw a purple one before. Or Holt, would you kindly demo again?
sure.
Do you have to retrieve your balloon?
I already got it. That's what
Okay.
I bent down for. So then you're going to blow it up again.
Oh, yep. Some people brought their balloons. They came prepared.
Same thing, hold it,
Mhm.
but this time you're going to have the balloon facing in a different direction. So I'm going to have the opening to the balloon facing down this time. Same thing, I'm going to hold it, and then I'm going to release. So as you might have seen a little bit of that, the balloon does not just go straight up, it spins around, goes side to side, and this one ended up on my right.
Sorry, a yellow balloon just went flying by.
Yeah.
In a circle.
So you'll see they're not very predictable at all.
If anybody wants to put their test results into the chat. So if you don't have your camera on, we don't see what your balloons do, but if you want to put your findings in the chat, that'd be great.
Either tell us how far it went or didn't go. Which direction did it go?
And maybe you have a different shape of balloon.
I want to see the, whoa, the purple balloon just took off.
Good one, yellow and purple balloons.
And we have one in the chat box that just went in circles.
Hmm.
Excellent. So would we agree that this is not ideal for
A rocket.
rockets?
Yeah, I think it's safe to say you would probably not get to the moon with a flight path like that. I think you might end up in somebody's backyard.
You hope.
Yeah, that
Holt,
might be.
Do you want to do the longer balloon right now?
Yeah, sure.
And then
So
also could somebody explain some physics behind this?
Oh,
Yeah,
it's an orange
uh,
balloon.
We'll talk more about the physics between balloons and rockets shortly here after everyone's flown their balloons, but pretty much when the air goes out of the balloon, it gets pushed out and makes the balloon fly. And since there's nothing on the balloon to help it be stable, it just goes in all the directions. We're going to see Holt blow up a much bigger balloon here. And since it's a bigger balloon, it can hold more air. It'll fly way faster, way longer than the little balloons.
this one takes a while to pump up. You have to use a special pump for it. All right, that's probably good. So with this balloon, you'll see it's very long and it has a little tip at the front of it. This is to add a little bit of weight to the front and it makes it more stable. And also the fact that it's longer makes it fly in one direction much better.
Sydney has a huge blue balloon.
So here, I'll launch it and hopefully you can see it
All right,
goes.
hold on.
Wait.
I'm gonna spotlight you so that everybody
Yeah.
sees you.
All right.
Does that work? All right.
Yeah. So this balloon, as you can see, is much more rocket shaped. So in theory, it should fly in a semi-straight line and go much further. And 3, 2, 1.
Whoa. Well, it almost like swam off camera.
Yeah. So there you
No
can see
motion.
it still spirals a little bit, but that one has a little rubber piece at the end. So the air stays in for longer and it has a longer flight. So that one you could see basically just went the direction I was pointing and then went up. So almost like a rocket.
Perfect. Let's
Okay,
Look at-
so has everyone flown their balloons?
I highly recommend if you can get some of those longer balloons, give it a try and see how far can you get a longer balloon, and how straight of a line will it go in versus your regular party size balloons?
So the balloons did fly similar to a rocket, but not very well. Does anyone in the audience want to tell us why that happened? Why they don't fly very well?
I mean, I'm happy to answer, but I want to see somebody else answer. Or you can type it in the chat box if you know the answer. But
You can guess too.
so Sean, the question again?
If
Well-
so the balloons did fly, but not very well. Does anyone know why they don't fly very well?
If I were guessing,
Oh,
we
here's
have
one.
somebody. The opening of the balloon makes it unstable.
Sort of, yeah.
I was going to
Thank you,
say the same
Joshua.
thing. Yeah.
Yeah. The balloons don't have a lot of force with them by just pushing air out. And that's one of the reasons they don't fly very well. But compared to rockets, one of the reasons, one of the big reasons compared to rockets that balloons don't fly very well is stability. Balloons are like rockets, but with no fins. Fins help the rockets be stable by making drag at the bottom of the rocket, causing the center of pressure to be lower. The center of pressure is all the air forces that are on the rocket. That's the one point where it's the most even. So if you look at me here on camera, I have a rocket here showing fins. So we have a rocket here with the fins. These fins here make the center of pressure right about here. That's where all of the air forces on the rocket, the entire rocket, that's where they're kind of the most even. It's the center of it. And stability, the rocket is stable when this center of pressure here is behind the center of gravity. And who can tell me what the center of gravity is?
Again, you can put it in the chat box.
Yeah.
I just know that gravity has something to do with objects being pulled towards the Earth. That's my scientific thought of the day.
Yep. So it has to do with the weight of the rocket and all the weighting of the rocket. Feel free to speak too if you want to answer the question. Well, the center of gravity on a rocket is the point where the rocket balances on both sides. It's where there's equal weight on both sides of the rocket. It's not the middle of the rocket. Yep, Sydney just said the place where the weight is equal on both sides. That's correct. So on this rocket, the center of gravity is somewhere around here. You can see me holding it with the finger there. And that's where there's equal weight on this side and equal weight on this side. It's not the middle because parts of the rocket are empty, parts of the rocket are heavier, like with the fins, and that's the center of gravity. So with the center of pressure being down here and the center of gravity being up here, the center of pressure is below the center of gravity, towards the bottom of the rocket, and that makes this rocket stable. So if we come back to our picture here, the screen share, there's some pictures here that show how stability affects a rocket. Holt, do you want to talk about those?
Yeah. All right. So here you can see there are two rockets pictured. The one on the left is very stable and has a straight flight path, as you can see. And then the one on the right has a very squiggly flight path. So the one on the left is more like an actual rocket that Sean showed. The center of pressure, which he was talking about, is below the center of gravity on the rocket, and it also has fins to keep it stable, whereas the rocket on the right doesn't have any fins, and the center of gravity is below the center of pressure. The rocket on the right is a lot more like the balloon you probably launched.
Yep. So for stability, to make something stable, you have two options. Either make the fin area bigger. You can see the fins on my screen here. You can either make the fins bigger, or you can add weight to the nose cone, the tip of the rocket, to move the center of gravity. So by making the fins bigger, you can move the center of pressure down. And by adding weight to the top of the rocket, you move the center of gravity up. And remember, what we want for stability is the center of gravity being higher than the center of pressure. So those are your two main options. Of course, you can get rid of weight towards the bottom to also make the center of gravity go higher, but that gets pretty difficult once the rocket's already built. I can't take a fin off of this to make it lighter. And that's pretty much covers stability here. Feel free to drop any questions in the chat. And let's take a look at a rocket that isn't stable, because just because a rocket has fins, that doesn't make it stable on its own. The center of gravity has to be higher, and the center of pressure has to be low. And sometimes when a rocket isn't stable, it'll act a lot like the balloons you've seen. Can everyone see the video? Everyone see that?
Mm-hmm.
Yeah. So Susan was asking, oops, where did it go? If you can change the, she was saying,
So,
yeah, go ahead.
Susan's question is how you find the center of gravity and the center of pressure. So for the center of gravity, you can just hold the rocket and bounce it. To get the center of gravity for your flight, you have to have it fully loaded, fully packed. You have to have your motor in and all of that, so you get the correct center of gravity when it's about to fly. And then you just balance it. And typically the center of gravity is measured from the nose cone, from the tip of the rocket. So this is maybe 23 inches from the tip of the rocket. Now, center of pressure is a lot harder. You cannot really calculate it on your own. You have to use special software. There's lots of tools out there to calculate the center of pressure of your rocket. One of the big tools that we cover in our STEM lessons is OpenRocket. And that lets you design your fins. It lets you design your whole rocket, including the fins, the weight, everything. It'll give you an estimate of your center of gravity, but that estimate won't be very true, won't be very close to real life. When you build your rocket, it'll be a different weight than what you predict it to be, and everything will change. But the center of pressure will stay pretty much the same as long as your fins are the same shape and size as what you designed it to be. And that's pretty much the only way to calculate the center of pressure. There are some other tricks you can do with involving strings and like hanging the rocket and like tilting it and seeing how it rotates. That lets you calculate it. But for rockets like this, that's not very practical. It takes a very long time, and just using a computer to calculate it is very quick and almost always very close to correct. I hope that answers your question. There's a link to OpenRocket in the chat here. You can download that, set it up, and try designing your own rockets. So we'll just show this video one more time of a rocket when it's not stable, like the balloons. And you can see it goes twirling in all sorts of directions, just like the balloons do. It's not stable enough to fly in a straight line.
Sean, was this a early design of a rocket or?
No, it wasn't. This was our late design.
Oh.
This was right before our qualification flights.
Oh, that's.
What happened was our rocket was a bit too heavy, and it did not work right. So next we have a short video here showing how rockets fly and all the parts that make a rocket fly. There's lots of videos, lots of words in here that really illustrate the points. And then we'll come back and show some more demonstrations. Let me know if nobody can hear it.
Model rockets are smaller versions of real rockets, and they use many of the same principles to fly. Model rockets are powered by a small motor that provides the thrust needed to make the rocket launch. Model rockets use what are known as solid rocket motors to fly, similar to what was used on the Space Shuttle and now the Space Launch System. Most other rockets use liquid-fueled engines. In liquid rockets, they mix two liquid parts together in a very complex engine. These two parts are the rocket fuel and the oxidizer, which when mixed together and ignited in the engine make a very powerful combustion or controlled explosion. Solid rockets have these fuels pre-mixed in a kind of waxy mixture, making them very simple. Solid rocket motors' simplicity makes it possible for anyone to make and fly their own model rocket. In amateur rocketry, these are referred to as rocket motors or just motors. When the motor is ignited, the solid mixture burns, producing a hot and high-pressure gas. This gas is expelled out of the engine very fast, producing thrust that propels the rocket upward. After all of the rocket fuel is burned, the motor stops producing thrust, and the model rocket will no longer be gaining speed. This is called motor burnout, the point where the rocket motor stops burning. After motor burnout, there is a part of the motor called a delay grain that starts burning very slowly. When the delay grain is fully burnt through, it hits the ejection charge, a small amount of black powder that burns and makes a high-pressure gas inside the rocket. This ejection charge gas forces the rocket to separate and pushes the parachute out. A lot of the time, you will use the ejection charge that comes built into the motor, but in high-power rocketry, separate computer-controlled ejection charges are common. The speed of the model rocket is determined by the amount of thrust produced by the engine. The more thrust produced, the faster the rocket will move. However, a lot more goes into the speed of a model rocket, including the size of the rocket motor compared to the size of the rocket. If you put too small of a rocket motor, it might not even leave the ground. Generally, the faster a rocket goes, the higher it will go. However, gravity will always be pulling the rocket down. And after the motor burnout, it's only a matter of time until the rocket reaches its highest point. The highest point of a rocket's flight is called the apogee. Another important factor in model rocket flight is aerodynamics. The shape of the body of a model rocket is carefully designed to minimize air resistance or drag. This allows the rocket to fly more efficiently and reach higher altitudes. The fins on the body of the model rocket are used to stabilize the rocket in flight by cutting through the air and keeping the rocket from tumbling. The fin shape can be designed to create less drag, further increasing the apogee of your rocket. To make sure model rockets are safe, strict safety guidelines must be followed when launching them. This includes making sure that the launch site is clear of people and obstacles, and that the rocket is pointing straight up into the sky. It's also important to make sure that the engine is the correct size for the size of the model rocket, and that the rocket is not overloaded with extra weight. In conclusion, model rockets use many of the same principles as real rockets to fly. By understanding the basics of how model rockets work, we can see just how amazing and complex this technology can be and learn a lot about physics. Just remember to always follow the safety guidelines and have fun.
Had some technical issues with that video there, but hopefully we're all back.
And Sean, to let everybody know that these videos will be available for people to watch at a later point, correct? That these are going to be made available to everyone participating in the rocket kits.
Yes, all these videos, this video and more coming soon are out on the Morris County 4-H YouTube channel. And then there's also written articles that are available to the people who got the rocket kits, and those will also be on our website soon.
And we can share that with all the participants today as well.
Yes, we'll share that at the end here.
Perfect.
So next we're going to talk about rocket motors a little more. We have some demonstrations here. On my presentation here, we have a little animation showing how rocket motors burn. The rocket motor it's showing is called a C6 rocket motor, and I have one of those here in my hand. It shows how the propellant burns. It shows how the propellant burns, and then how it burns this little delay at the end, and then it does this little ejection charge right towards the top, and that puts gas into the rocket to make the parachute deploy. So we can look at this here. At this end, this is the nozzle where the flames come out to begin with. And then at the back end here, you can see the little ejection charge that fires at the end. So this part sticks out towards the bottom of the rocket. And then up here, that's in the rocket. And that'll fire the parachutes. Next, Jonathan, are you here?
Yep.
So we have a couple other size rocket motors here. So like I just showed you, this is a C6 rocket motor. If people were at our launch a couple weeks ago, you were flying these 1/2 A's. These were also the rockets that came with any of the kits that we delivered. So the C6 is a little bit bigger than these 1/2 A rocket motors. That's because rockets have impulse classes which go off the letters. Jonathan's about to talk about that more. And then this is a C motor, right? And then the bigger the letter, the bigger the motor. Then here we have a K rocket. So this little C rocket is one of the most common model rockets there is. But then we have this K, a very large motor, and this is what we use for our competitions. Jonathan, can you explain the difference between these rockets a little more?
Sure. Like Sean said, each letter defines its impulse. So for example, let's say, I believe that rocket motor was a K1000. So the letter defines its impulse, or no, the higher the letter, the more powerful it'll be. So after the letter comes the number. So for example, that was 1000. So that means it has 1100 let's just say thrust, which is also impulse. With the 1/2 A's, they're much smaller. On scale, the 1/2 A's are 1000 times less powerful than the K motor. And so you'll have A motors. Well, to answer your question, there's not really like a limit. I guess it would be like Z, but then you have like all these letters that you have to like make because they don't sell anything past an O, I think. Continuing, they're different and similar because they both, well, 1/2 A's use what's called black powder in the motor, and with most bigger rockets, they use composite. So one's more powerful, one's not. And they both have different delay charges. But with the K motor, you have to set your own delay charges because with conditions in weather that can affect that. With the 1/2 A's, they come with a set delay charge, which you want to buy on the day of the launch because then you have a higher chance of recovering it. The delay component, so as you can see the animation there, the propellant burns and then that burns until it goes into the delay propellant or delay, which then as Sean showed in the C6 motor, when you launch a rocket in low power, which is C6 or anything under that, it goes propellant, delay, ejection. The delay emits a smoky trail that makes it easier to track so that you don't have to go rocket hunting. And then after that, the delay element ignites the ejection charge, which pops out the parachute. It's the same
John,
thing with.
Okay, if the delay wasn't there, the parachute would come out right after the motor has burned.
Yeah, you don't want that because
Right, that would not be good.
yeah. So what happens? Holt showed us in the video. The delay element kind of continues to the apogee, and then you want the ejection charge, because if you do it right after the propellant, it will most definitely destroy your rocket because of the speeds. You're welcome. That sums it all up.
Yep. So pretty much each letter, the higher it goes, the double the power. So a C is quite a few letters short of a K. So each letter, it doubles and doubles and doubles. There's a few levels of rocketry. Anyone can go out and buy this C6 at any store. That's a model rocket. You can just buy and fly anything up to a G motor. Then when you get to bigger motors like an H or an I, again, each letter, they double in the total thrust. So H and I motors are starting to get pretty big. They're not as big as this K here, but they're still pretty substantial. So H and I are considered level 1 motors. You need to pass a test and complete a successful demonstration to prove that you can safely operate those. And then K, J, and L motors are level 2. So then you need to take another test, another demonstration with these size motors. And if you do that successfully, you can then fly and operate these and buy them. And then there's one last level, which is level 3. And that's M, N, and O motors typically, and bigger. And that's pretty much the limit for commercially available motors. Like John said, there are more motors common, N motors, S motors. Those are both ones you see quite a bit, but they more often than not have to be custom made by hand and usually need other precautions before you can fly them. You might need to notify the Federal Aviation Administration if you're flying very high, or other government bodies that you're conducting such a powerful test. It's like an S motor might be 12 feet tall, just 12 feet of pretty much what are explosives. And some precautions need to be taken to use those safely. But for anything under an H letter motor, anyone can go and buy those and fly those and enjoy rocketry. I'm seeing in the chat, Kelly's asking what size rocket we're launching at SLI in April. So this is the motor we're using. It's a K motor. The classification, like John talked about, it's a K motor impulse class, which just summarizes all of the potential thrust in that class. And that's a 1/1000 rocket motor fuel. And the number there, 1/1000, is the average thrust for the whole burn of the rocket. So this rocket burns for something over 2 seconds, and the average thrust over the entire burn is 1,100 newtons. If we take this C6 motor back, it's a C6. That means it's a C class for total thrust, and it's a 6 for the average thrust. You can see on this video here, it burns for 2 seconds, and you can see the little chart of the thrust it produces throughout its burn. There's a little bit higher thrust in the middle, and it falls off towards the end, but then it makes an average of 6 newtons over those 2 seconds. So the balloons that are making the news right now, there's lots of different sizes. Some are just amateur balloons, which might be 3 feet wide. The balloons aren't powered by anything. They're tied up and they float. It depends on the design of the balloon. I'm not a balloon expert, but they're a bit different than rockets. Yes.
So, Sean, I'm just keeping an eye on time.
Yes,
and I know that
yes.
all of our questions are. I know we're so interested in what you guys have to tell us, but I know that you had some more pieces to go over with us.
Yep. Okay, so now we're going to briefly talk about how to prepare a rocket for flight. Again, if anyone has questions, let us know in the chat, or you can unmute and ask right away. So here we have our TARC rocket. For those who were with us 2 weeks ago for our group launch, we flew this right at the very end, and it was a very nice flight. So to prepare this rocket, there's a few things going on. Towards the top here, we have the eggs. This is for the American Rocketry Challenge, and the main goal there is to have a rocket that flies eggs. So the first thing we would do on a launch is we take this top part off, and then we take these little pieces of foam that are in the this top piece here. You can see it's hollowed out in there, and then across this with the 2 eggs would go. We have these pieces of foam, which are the size of half of an egg. We'd use 4 of these. An egg would rest in them, and then another piece of foam would go over it. And then we stack those in here, push it down, put a new piece of foam, put the next egg in that, put another piece of foam on top, and it's done. And then, again, this is last year's rocket. One of the requirements last year's competition was to have body tubes that were 2 different sizes. So if we look at this, we have the top body tube here and then the bottom piece, and you can see that they're different sizes. The top is a bit bigger than the bottom. So here we have this transition piece. It adapts the smaller piece to the bigger body tube. Everyone can see that. So next, what we would do in this little transition piece here, it's pretty much an empty plastic cup. We put a little computer. We put a little computer in this transition piece, and then we close it up. We put the upper piece on, line up the paint so that we can line up the screw holes. If you look closely, there's various holes around the side where we put screws in so that this upper piece and our eggs don't come out during the flight. We don't want to make scrambled eggs. So our next step would be just screw those screws in, make sure that the rocket is secure, these eggs are safe. And then we start packing this. So towards the bottom of the rocket here, I'm going to set this egg piece aside. These eggs, the only problem here is that there's a computer in here that runs off of a battery. So we don't want to let this go too long, but it can still wait for a couple hours. On our launch that Saturday, we put this together before anyone got there, and the 2 hours, it was still working perfectly. So next we're going to focus down here. So one of the main pieces with our rocket here, the goal of the competition is to take those eggs to a certain altitude. That was 850 feet. So rockets can be very sporadic and volatile. So depending on the weather, the wind, the temperature, all of those will change how high your rocket goes and how fast it goes. And we have to fly on all sorts of different days. So every team needs to have a system or some kind of way that they can adjust their altitude depending on the conditions. Because the goal is to get exactly to 850 feet. So what we did is we had this little small piece that just goes on the back of the rocket and sits there for the flight and changes how the rocket flies. Does anybody know what this does to the rocket?
Mm-mm.
No idea.
So this little plate back here, I'll give you a hint. If you look down there, you can see it kind of sticks out a bit.
Does it create some drag?
Yes, it does. So what we would do is we'd have a bunch of different sizes of these plates. all very little differences between them so that we could get as close as possible. So on launch day, we would look at the conditions, we would do some calculations and figure out which size of these plates would be ideal. And then we would install the right size, would go right back here, and then it would create drag on the back of the rocket, just slowing it down a little bit so that we get the exact size that we want, exact altitude. So that's one of the first things we would do. We would calculate that with the wind, temperature, everything, and then we'd put it on. And then what we'd do next is we would install our rocket motor. Last year, we used the F-25 rocket motors. Again, the rocket classifications, that's a few steps above C. But as you can see, it's still pretty small. It's a model rocket. So we put that in the bottom. It sits in there. And then we take this little cap, screws on. This is called the motor retainer because it keeps the motor, keeps the motor from coming out, kind of blocks the motor there. It also helps screw on the orange plate we have back here, keeps that from coming out, and everything back here is very solid. And then we're done back here. Everything's good. Next, if we take these pieces out, we have the parachute and the little protector here. So like Jonathan talked about, the rocket motor will fire a little explosive inside of the rocket that forces the parachutes out. It makes very hot gas. And this parachute here, which is made out of, I believe, ripstop nylon, it's pretty much plasticky. It'll melt. This rocket actually has some melt holes. No matter how much protection you put in that rocket, there's still a lot of heat and parachutes melt. So what this little piece does here, this is called, Holt, remind me what this is called?
That piece right there. Oh my goodness, that's my favorite. That is the flight napkin, as I like to call it, or the technical term for it is a Nomex blanket. It's like a fireproof material. It's the same stuff they use in fireman suits.
Yep. So that just goes, we push it way down to the bottom of the rocket, right where the motor ejection charge will be, and that helps protect everything in front of it, which will be the parachute. There's also some other wadding you can put in here. If you've flown model rockets before, you might have seen some fireproof paper that you put in the rocket. Sometimes we use like housing insulation that's fireproof. We just put a bunch of that in there, and it also helps protect the parachutes. So what we'll do next is we will pack the parachute. Important. The parachute's very important because if you don't pack it correctly, it might not come out. It might come out tangled. If you don't pack it correctly, it's not going to come out correctly, and your rocket will not land safely. It might not come out at all, in which case your rocket will hit the ground very hard, or hit some property, or hit somebody very hard, and that is very important to avoid. So going through and packing it here. First, we start by just folding the parachute a couple times, makes a nice triangle. Then we'll take the parachute's lines here. We just kind of place them inside of the parachute triangle here. Just grab those. And with those lines in here, we're going to fold it in half, tuck the lines away. We're going to fold the parachute in half again. And again. And the lines are no longer hanging loose like they were before. They're tucked inside the parachute. So when the parachute gets pushed out of the body tube, this will unravel. The lines will be free to come out naturally. If we wrapped the lines around the parachute, well, the lines can get tied out. They're getting spit out very fast. The lines can get tangled up and keep the parachute from opening. But this way, the parachute will open no matter what, as soon as it gets pushed out, and then so the shock cord, and we tuck that in. Here Take the remaining shock cord, tuck that in. And the upper piece just goes right onto the body tube here. We don't put screws in here because we want the rocket to separate right here. So if we look at this, how it would open in flight, and then this piece gets shot out pretty fast, and it pulls all the lines in here out with it, including the parachute. And that's how we pack our rocket. The last thing you would have to do before launch is put the igniter in here. You'd put a little tape over it to make sure the igniter doesn't fall out, but that's all. And then your rocket's ready to fly. You put it on the launch pad. We have the rail buttons up here. We won't go too far into that, but this is where it goes onto the launch pad. But since we have a bigger piece up here, if we put the launch pad on the smaller side, it would just get stuck up here. So we have to attach it to the pad at the top where it touches the launch pad. This isn't how most rockets work. Most rockets will have it at the bottom. But since we have a bigger piece up here, we had to do it like this, unfortunately. Any questions about how to pack the rocket, prepare it for flight?
Oh, that was cool. Never seen a rocket disassembled like that.
Okay, and I will reshare my screen here. Now, does anybody have anything they want to talk about briefly? I know we're at the end of our time slot here.
So, Sean, I have a question just as somebody who's never done rocketry, and this is really to, I guess, the whole team of just, you know, like okay, I've attended something like this and I'm interested in rockets, like, do you recommend getting started on those big motors and stuff, or is it better to start off with some of the like smaller model rockets? Like, how do you get started in this?
Well, that's really up to you. The bigger rockets are a lot more expensive, but they're also kind of easier to make. If you go out and find like a level 1 rocket kit, it has all very big parts. The fins are big, the slots are big. They can be more forgiving rather than having to fiddle with very tiny pieces. They're all like this big. So that's one way you can go. You have to be 14 to do level 1 rockets. But of course, you can start with smaller model rockets. There's lots of easy kits you can go and get started with and learn the fundamentals. And that can also be a really great way to get started.
Awesome.
So it's
And
really up
Sean-
to what you want to do, what you have available. Because bigger rockets, you need to go to a dedicated launch site for. But smaller rockets, you can just launch in your front yard.
I don't know. I think my neighbors would freak out. Might want to give them a heads up. What about from everybody attending today? Any questions on the group? This is your chance to ask somebody what you've always wanted to know, a burning question about rocketry. Susan and I've been chatting away, asking you guys questions. Does anybody on today have some of the rocket kits? As the team mentioned, that part of the STEM outreach, STEM engagement was to send out some of the rocket kits. So if you have one, if you received one, can you put it in, let us know in the chat box. We know that they went out to lots of different groups all over New Jersey. And I'm just gonna see if I can find real quick, if Sean, if somebody's interested in getting those rockets. Those were, what are they called?
They were,
Genome.
yeah,
Genome.
SD's GNOME rockets.
GNOME rockets.
Genome.
Genome. All right, I've just been dropping lots of links in, so, you know, there's another one. If anybody's, even if you were like already ran through all 12 rockets in your kit, now you want more. Yep, Ocean County got some. Yay, Camden County got some. Exciting. All right. So Ocean County, Camden, since you guys have the model rocket kits, any questions for the team today? Otherwise, I know the team, you guys have your contact info. People can send you some questions as they come across them, correct?
Yes. Yep.
How's the best way to reach you guys?
The best way would be email. If you go on our website, nj4h.space, we have contact information there, and that's one of the best ways. Otherwise, if you don't go there, our email is kind of long. It's ResistoJet Rocketry, all one word, lowercase, @gmail.com. And that's pretty much the only way to reach us.
Trying to find your email, but just unless somebody from the team wants to just put it in the chat box real quick. We are quickly, well, we're technically over our allotted time, but thank you guys so much for sharing so much great information, for everyone staying on. When you leave today's Zoom, there should be a three-question survey. If you wouldn't mind just taking a moment to answer, this will help the team get a little bit of feedback and help them with their STEM engagement reporting to NASA. All right, I'll put it to the team of any final thoughts or anything you want to share with the group before they all disappear and get launching.
There was a question here where to get the kits. There might be another launch at Highview Farms, Evan, and then if that is the case, we may have some more kits available. Or you can get them online, ask your parents.
Yes. And I do know that they're in conversation with other counties that there are model rocket clubs throughout the state. They would love to get connected with any local residents, participant, anybody who would love to get started in rocket launching. So take a look around, reach out to your local enthusiast clubs and hobbyists, see what they got going on. All right. So stay tuned for more videos, right, Sean, that you guys are going to be posting some more on your website and various other places.
Yep. They'll be on the Morris County 4-H YouTube account as well.
Excellent.
The resources will also be up on our website soon.
Excellent. So excited. Hope to see lots more rocket launches happening throughout New Jersey. All right. We're technically over our time, but it's been a delightful time together. Happy launching, everybody.
Yeah. Thank you, everyone, for joining us.
Yeah.
Really appreciate it.
I guess we can stop recording.
Have a